Why do we use modular arithmetic? Well, it's to work with smaller numbers. For example, to measure time since the Big Bang. We don't say that there are 31,536,000 seconds in a year, or there's 435 quadrillion seconds since the Big Bang. We say 13.73 billion years. The foundations of modular arithmetic were introduced in the 3rd century BCE by Euclid in the 7th book of his Elements. Modular arithmetic, or as it's sometimes referred to as even clock arithmetic, is in its most elementary form arithmetic done with a count that resets itself to zero every time a certain whole number, such as n, is greater than 1, known as the modulus or mod, has been reached. An example is seconds. Every time 60 seconds passes, the count resets itself to zero to start again and indicate the start of the next minute. Modular arithmetic is important in number theory, where it is a fundamental tool in the solutions of diaphonic equations, particularly those restricted to integer solutions. Under modular arithmetic with mod n, the only numbers are 0, 1, 2, up to n minus 1, and they are known as residuals module n. These are added by taking the usual arithmetic sum, then subtracting this modulus from the sum as many times as is necessary to reduce the sum of the number m between 0 and n minus 1. M is called the sum of the numbers module n, such as if you had a 21 mod 9, then you would subtract 18 to take the number below the mod, which in this case is 9, so 21 mod 9 equals 3. Example of this use of modular arithmetic occurs in ancient Chinese, Indian, and Islamic cultures. In particular, they occur in astronomical problems, since these involve cycles, but one also finds modular arithmetic in purely mathematical problems. The Chinese remainder theorem is a result about congruence in number theory and is generalization in abstract algebra. It is an ancient theorem that gives the conditions necessary for multiple equations to have a simultaneous integer solution. The theorem has its origin in the work of the 3rd century AD Chinese mathematician Sun Zi, although the complete theorem was first given in 1247 by Qin Jinxiao. In its basic form, the Chinese remainder theorem will determine a number n that when divided by some given divisor leaves given remainders. For example, what is the lowest number n that when divided by 3 leaves a remainder 2, when divided by 5 leaves a remainder of 3, and when divided by 7 leaves a remainder of 2. An example is someone is asked to find a number that leaves a remainder of 0 when divided by 5, a remainder of 6 when divided by 7, and a remainder of 10 when divided by 12. The simplest solution is 370. Note that this solution is not unique, since any multiple of 5, 7, and 12, which equals 420, can be added to it and the results will still solve the problem. Tazu's work contains neither a proof nor a full algorithm. What amounts to an algorithm for solving this problem was described by Aryabhata. Special cases of this Chinese remainder theorem were also known by Brahmagupta in the 7th century and appear in Fibonacci's Liber Akbar in 1202. The existence and uniqueness of this solution can easily be seen through a non-constructive argument. There are n equals n1 to nk different k tuplets of remainders. Let us call this set R. On the other hand, n equals numbers 1 to n, and each element of 1 to n corresponds to an element of R. Can two numbers a, b include 1 to n correspond to the same member of R? That is, can they have the same set of remainders when divided by n1, n2, up to nk? If they did, then a minus b would be divisible by each n. Since the ni are relatively prime, a minus b would be divisible by their product, n. But as 0 is less than or a minus b is or less than n, this can't be. So this function this function 1, 2, 3 up to n in goes into R is 1 to 1. since numbers 1 up to n equal numbers r. It must be onto as well. Thus we have established the existence of a bijection.
Okay, so here we have the basics of modular arithmetic. So we have this equation a divided by b, where a and b are positive integers, and that gives a result of q, where q is a quotient, remainder r. And that translates in mod arithmetic to a mod b, which equals r. So you're effectively taking the a, the b, and the r, and removing the q value. So if we take an example of 17 divided by 5, that actually gives 3 remainder 2. So just to prove that, you do 5 times 3 equals 15 plus the remainder of 2, and that gives you 17. But in mod arithmetic, the r value of 2 will actually carry, so you'll have 17 mod 5, which equals 2. Alright, calculations using a calculator. Okay, so you have this equation 66 divided by 7, which is approximately equal to 9.43. But 9.43 in modular arithmetic doesn't exist. You remove the decimal, so effectively 0.43 is a remainder rather than a decimal. So you've got this equation a divided by b. Now, in this equation, you've removed the remainder because you're going to use the calculator to find the remainder. So in this case, a would be 66, b would be 7, and from below, you'll take q equals 9 as an integer value and remove the 0.43. Now, you haven't solved it. You've got to find what 0.43 is in modular arithmetic. So you're using this equation. So effectively, this will be 66 minus 9 times 7, and that'll give you the remainder, which is what you're trying to find using mod arithmetic. So this will form 66 minus 9 times 7. 9 times 7 equals 63, so it's going to be 66 minus 63, which is actually 3. So therefore, as r equals 3, in modular arithmetic, you'll find 66 mod 7 is equal to 3. Okay, so now you've got your feet wet. Let's do some arithmetic involving actual addition. So let's take 214 plus 163, and let's use mod 13. Now this will actually equal 377. So using the method from before, we'll just go through it slowly, and you'll find that it's 0. So effectively what's happened is you've done 377, which equals a, you've done b, which is equal to 13, and q is equal to 29, and you'll find x is equal to r, which equal to 0. So effectively 377 mod 13 is actually equal to 0. Now this alternate method is it'll seem much slower in this case, but with numbers that a calculator can't handle, it is actually a better method because it's making the numbers smaller, and it's actually a lot more helpful in some ways. Okay, so for this alternate method, effectively what we're doing is, rather than finding the modular of 377, we're modulating 214 and 163. So you'll have you'll find that x in this case is equal to 6. So 214 modular 13 is actually equal to 6. Now following from this, 163 modular 12 is equal to 7. Now following from it, we'll take that, okay? And we'll go x equals 6, y equals 7. Now before it said that you're adding them. So 6 plus 7, x plus y equals 13. But what's 13 modular 13? That equals 0. Therefore, 214 plus 163 mod 13 is equal to 0.
Okay, so the conclusion that we take from modular arithmetic is that it introduces a new congruence relation between different integers. For example, 34 is congruent to 14 in modulo 12. You can also apply other operations to these numbers, including addition, subtraction, and multiplication. Division is a whole other topic which is covered by Euclidean division. Modular arithmetic is also used in other places, for example in computer science, especially in cryptography. Cryptography is essentially data encryption and decryption. Modular arithmetic is used for the basics of computer security systems with encryption and decryption. There are multiple ways of doing it, such as Advanced Encryption Standard and the RSA method as well. They both use different ways to encrypt the data using modulus. Modular exponentiation is a type of exponent multiplication using modulus. The most common use is through RSA encryption key generation. Messages can only be decrypted in a limited amount of time using a private key. This private key is generated through modular operations, and an example of this is shown in the key in the bottom right. This key fob is used in businesses to access internal information externally, where this private key is only generated for a limited amount of time. This is where modular comes into play in the real world use and how it's impacted society. Key generation for RSA is done through these steps shown here. The conclusion that we take from this is both the public and private keys both consist in modulus n, but they both have different exponents, so one can't be calculated by using the other. It's only through the algorithm that it's used. The other method is Advanced Encryption Standard. This uses transformation of the data through different steps. The steps where modular comes into play is called the mixed columns round. The mixed columns transformation stage uses matrix multiplication done with modular polynomials. It's used to mix up the columns of the bytes of data using a fixed matrix. The columns themselves are treated as a polynomial and then multiplied in modulo x to the power of 4 plus 1. Everyday use of modular arithmetic for most people comes down to reading the time. This is especially for 12-hour time. For example, if the time is currently 9 o'clock, 4 hours from then will be 9 plus 5, which equals 14, but most people don't speak in 24-hour time, so they'll represent this 14 as 2 o'clock instead. As shown below, 14 modulo 12 equals 2, so that means the 14 will equal 2 o'clock. This can also be applied to calculating minutes and seconds, as they both run in modulo 60. Also, days of the week can be determined using modulo 7. For example, if Sunday is 1 mod 7, then 9 days from that will be Tuesday, which is 3 mod 7. Other uses of modulus also include being in music, where modulo is used for 12-tone equal temperament, where octave and enharmonic equivalency occurs, meaning that pitches in a 1:2 or 2:1 ratio are equal. C# will be considered the same as a D flat in this situation.